class, let's settle down and get started for today. CS 251. All right, starting off with a few announcements. Homework 5 was due today at 10 a.m. Hopefully, all of you completed that. We're having the labs meeting as usual, and then the next project will be coming soon. So make sure you are attending your lab sections. And today we're going to be covering stuff that'll be handy in the lab too. All right, so what are we talking about today in general is we're going to continue our discussion of binary search trees. We started off this Friday, we looked at binary search. On Monday, we looked at how binary search trees are implemented in code, what's the concept behind it, why we use them, as well as what we do if we want to search for a key inside of that tree. Any questions before we proceed with today? All right, awesome. All right, so when working with data structures and implementing them in C++, one thing that you'll commonly observe is that you'll have a combination of C and C++ core elements working together. For example, in this case, that you can see that we looked at this code on Friday. It's an implementation of the binary search tree class. You've got the class, you've got templates, you've got objects, instances, you've got member functions on those classes, you've got private members, you've got public, you've got constructors. All of these things are just specific to C++. There's no object-oriented programming in C, so you don't have classes and you don't have member functions and constructors and destructors and all that stuff. But an interesting thing to know here is that even when there's this class, you've got pointers. So when you think about C, you think about pointers, you think about memory allocation, you think about the heap, think about pointer arithmetic, all that stuff. So even though we're using the C++ infrastructure to implement the binary search tree class, there are elements of it that are going to be ones that are core to the C programming language. So, for example, in this case, you've got the node pointer, right, which is a private pointer inside of the binary search tree class, but it is essentially a pointer, and it's pointing to some object, some memory location on wherever the tree is implemented. So, have you covered the concepts of stack and heap in any other class? No, if you have. All right, so when implementing this, in creating insertions in that binary search tree, would it be a good idea to do it on the stack or the heap? Any ideas? How many people for a stack first? What about the heap? Yeah, awesome. Yeah, so again, the point to note is that the heap essentially allows you to dynamically increase the memory. So this becomes important when you're implementing data structures because let's say you're you're reading from a file and implementing a tree. And you might not know beforehand what's the length of the file and how big your tree is going to be. So in such cases, you're going to use something on the heap where you've got a free memory store where you can easily increase the size of your data structure. All right, so any questions about this implementation so far, how we're, and the understanding of how we're using C and C++ in combination to implement data structures, specifically binary trees in this example? All right, great. So another thing to note is that you should not hesitate to create private helper functions. So in this case example, we've got your in-order function. It's a private function, so it returns void. And what in-order does is that it's a recursive call to print out all the keys. at all the nodes, given a starting root node. So essentially, these pointers essentially the thing to note is that these member functions do not access root, but instead are passed to tree or subtree to work on. So you can also pass the subtree to have this function print out whatever values are in that subtree and not the whole tree. Right. So current pointer here can be any object, node object. Yeah. You will have to call that function. Well, yeah, you need to. So it's a helper function. So it will have a wrapper function that's publicly accessible. So you can't, because it's a private function, you can't really directly access it outside. You can't do like binary search tree dot underscore in order, but you'll have a binary search tree dot in order. And actually, we'll look at other examples of how you rewrite these private helper functions. There's another question. Another question. All right. Any other questions? All right. So just taking a quick look at this in order function and how it's being implemented is that it's taking a pointer of type node, and it's checking if the current pointer is null. It's returning. So that's essentially an indication that we've hit a leaf node, and there's nothing left or right of that node. There's null pointers. Otherwise, it would go towards the left branch, and it would print that out, and then it would continue on going, because this is a recursive call. So inside this function call, there's going to be another call to the left until it hits the leaf node, and then it returns, and then it prints out, and then it goes towards the right. So in order essentially a sequence of how you want the tree printed out, and in this case it's from left to right. So if we have an example of the tree here, so in order would starting off right here, in order would like come down here, it would print out, it would come all the way down to 3, it would print out 3, and then it would return, come out here, print out 19. Well, 3, 11, 19, return, 22, and then it'll start going to the right side. So see how whenever we're doing recursion, the thing to know that is you go all the way down to the bottom, and then when you hit the condition where, okay, there's no more of the tree to explore, that's when you start returning. That's our return condition. Any questions? Yes. If you want any on that operation on the whole tree. Does that make sense? Right. So yeah. Current's a generic pointer that can be used to perform that function on starting any node. So in this example right here, this is the complete tree, right? But this is also a complete tree, binary tree. So it's a subtree that's a part of the larger tree. So let's say if you only wanted to print this region or print this region, then you would just specify this as the current node and wouldn't care about 22. So that's a generic implementation of the function that allows you to perform that function on smaller subtrees. And that really becomes important when we're doing recursion in general, is because we'll see later on in the lecture that in recursion, every time you're doing a recursive call, you're performing that specific operation on a smaller subtree. That's how recursion essentially works. Any questions? All right, so there's essentially two ways to traverse a tree. Uh, the first one is using a simple loop or doing it through iteration. For example, we looked at on Monday was we wanted to search for a specific key inside that tree. So we did quickly going over the code here. You've got the current pointer that's pointing to null, and that's when you know you've hit the stop condition. You hit the leaf node. Otherwise, this is the true condition where you found that current key that you're looking for. It's exactly on that current node, the value of that key. Otherwise, if it's less than, this is a condition that's fundamental to the implementation of binary trees, is that everything that's smaller to that current node key is going to be on the left-hand side, and everything that's larger is going to be on the right-hand side. So because the binary trees order in some fashion. So if you're looking for that key that's smaller than the value of the current node, you'll go towards the left. Otherwise, you'll go towards the right. Simply what's happening in this case. So simple, iteration, for loop, while loop, based traversal of the tree. But there's another way that we can traverse tree. The one we just looked at with the in order function is through doing it with recursion. Now, an interesting question that comes up is that which one is better and which one should be used when? So before we suggest the answer for this, let's pose a question for the class. So when performing a tree operation, the first question to ask yourself is, which traversal do you use, right? So do you want to do loop or do you want to do recursion? Now suppose you have to perform three operations of binary search tree, right? So there's three distinct operations that we're doing on this binary search. So we're computing the height, we're making a copy, and we are removing a specific value on the tree. So these are possible options. I'll give you a few minutes to discuss with your peers, and let's say 4 minutes we'll come back and talk about this and see which implementation we use for which specific operation and what's the unique property about it, why we use it. All right, feel free to discuss. right, so let's uh, let's let's come back and see what's going on here. So how many for A? So A should be easily negated because we've done something similar to removal, which is search, and for search we already know that we use iteration. What about B? Okay. Uh, C. All right. Yeah. So yeah, C is the correct answer. That for hide and copy, we're using recursion, and for removal we're using iteration. Now, what's fundamental about these specific operations that we either choose recursion or iteration? So think of it in a way that every time uh, you have to look at the complete tree, you want to use recursion, right? For example, to let's say create a copy of the tree, you need to visit each and every node in that tree to be able to create a copy of it, right? Similarly for height, because for height you need to explore all the, the corresponding edges in that tree. That's when you'll know what the height is. You'll essentially need to look at the complete tree. So anything that requires a more of a holistic view or involves visiting all the nodes, for in that case you'll use recursion. So similarly that we use the in order function that we just saw, where we're just printing out the tree, but because we were printing out all the elements starting from that current root node, we use recursion. Whereas iteration or a loop-based traversal is used when you want to do some sort of specific operation on a certain node. So you have a key, you want to search for that key. You have a key, you want to remove that node that has that specified key. You want to insert something into that tree. So anything that's more specific, where you can ignore parts of the tree based on comparisons that you do on the properties of the binary search tree, you can use anything that's iteration related. So everyone clear on when to use when, and which one's better when, and which one performs when. Questions? All right. So um, let's say if we were to do the sum of all the all the nodes in the tree. So imagine like we have a tree that's all integers. The keys are integers, and we want to do a sum. How many people think that iteration would be a good idea there? Sum of all the nodes in the tree. Iteration. Anyone? Okay. What about recursion? All right. Yeah. So yeah. So I'm glad no one said iteration because again, sum it's a holistic process. You're looking at all the nodes in the tree. So anything that involves that, you want to do it recursively. Everyone clear? All right, great. So when traversing a single path, we use iteration or a loop inside of code. And then when traversing the entire tree, we perform recursion. All right. Any questions? All right, great. So let's have another question. So you're given this tree. We've been looking at this tree for quite some while now. What is the height of this tree? So take 2 minutes to discuss with your peers, and we'll come back and talk about it. All right, so let's let's come back and see what is the height. So how many people for A? For A, okay. Uh, what about B? All right, fair. What about C? Okay. Um, nine. Anyone nine? Okay. So no nines. Okay, great. So we got either 2, 3, 4. So um, the way height is defined is that it's the number of edges along the longest path in the tree, right? So even though you're looking at one edge, to figure out which one edge is that which has the longest path, you need to be able to look at all the edges, and hence the use of recursion. So the height in this case is 3. So 1, 2, 3, or 1, 2, 3. So if we, and that's on the right hand side. If you go on left, it's 1 and 2. So we look at 1, 2, 1, 2, 1, 2, 3, 1, 2, 3, 1, 2. So what's max? It's 3. So that's the height. Right. So it's a number of edges along the longest path. Everyone understands how we figure out the height. All right, great. So a couple of more questions related to height. So we'll do this collaboratively. So any guesses for the first example on the two for the empty tree? Someone in the back, Stein. No. Yeah. -1. Anyone else got any other guesses? 0. Okay, so we're tied on 0 and -1. So the answer here is -1. Uh, and we'll take a moment and understand. So why is that? So this makes it simple that the second option is obviously 0. So um, again, this is for use for reference. Is that because there is no root node, the tree is empty. We specify the height to be -1, so that when there's just the root node, you can specify the height to be 0. Because when there's just the root node, the tree's not empty. It contains one node, but are there any edges? In this case, are there any edges present? No, so that's why the height 0. And how do we define the height is, it's the number of edges along the longest path. What about this example right here, third? Yeah. All right, great. Yeah. So that's the height. So we've got 1, 2. We've got this path, and we've got this path down the tree. So all right. So now that we've got an understanding of how we do and calculate the height of given a binary tree, let's look at how we would implement this inside of code. So here's one possible implementation of the height function. The function isn't working, unfortunately, because it always returns a 0. Now there are two errors. Your job is to ideally spot both of them, but let's say if you could spot one. So these are some possible options. Take a few minutes, discuss with your peers, and then we'll come back in a few and collectively discuss which of these options are the reasons why this tree is not calculating the height correct. This function. All right, feel free to discuss. All right, take 2 more minutes. All right, so let's come back and go over each of these options and see which ones are essentially the reason why this is not tree is not implemented the height function correctly. All right, so option A, incorrect when tree is empty. How many people think that this is a reason why it's a possible source of error in the code? All right. Right. So we just discussed it that when the tree is empty, what's the height of the tree? -1. And then we don't essentially see in this case that if this function was passed the root pointer, and then the root pointer was null, which is the standard case for an empty tree, the height would be returned -1. Right. So yep, this is one of the. Now we're one down. Okay, so. Select a pen. All right, so what about B? Anyone for B? Okay, good. Yeah. B doesn't seem to be a reason. Recursive calls should be calling height and not underscore height. Well, the point to note is because it's a recursive call, and how recursion works is that. So before we actually target this, let's look at the difference between height and underscore height. So height is the outer function, and then underscore height is essentially a helper function that takes in a generic standard pointer, right? So what we're doing here is that to have the recursive calls, each recursive call needs to have an argument. So in this case, height is not taking any function parameters or function arguments. So that's why this is not a reason. All right. What about C? This code fails when height of the left-hand side is equal to the right-hand side. Anyone think this is an invalid? There's a reason why this code's not working. All right, yeah. So this the comparison is irrelevant, and the reason behind that is because we're concerned with the height. It doesn't really matter if that height is coming from the left branch or the right branch, as long as they're equal, right? So in this case, because we're comparing left with right, well, we're always going to return the left-hand side. But let's say if we went back here, and in this case, let's say there's another node here, all right? So let's say we've got one here, right? And then we're going to compute the height of the tree. So at this point, when we get here, both the left and the right each have one edge, right? So height of left is going to be equal to the height of right. But what it's going to do is it's just going to return the height of right and not the height of left. But does it matter? No, as long as they're equal, it doesn't matter. So Again, C is not an option. All right, what about D? How many people think D is incorrect? Okay, but I mean incorrect is like it's not a possible source of error. Okay, well, interestingly, excuse me, interestingly, D is a valid reason why this code is not working correctly. So, if you look at the code right here, on each recursive return, are we incrementing anything? No. So we're not essentially keeping track of height or how deep we went inside the tree when we're trying to return, right? So how recursion is working is that we're continuously doing recursive calls to the bottom of the tree, and when we hit the leaf nodes is when we hit this condition is when we start returning. So we return 0, right? When we return 0 when it's a leaf node, but when it's an actual edge, are we counting that edge? So what needs to be changed for us to be counting every valid edge? Yeah. Right here or right here? Okay. Yeah. Yeah. Exactly. So you could either add a +1 here, or you could do a +1 here. So every time you're returning it, before you return, you increment the height, right? So you're keeping track of both the height and the left branch and the right branch, and then on each iterative recursive comparison, you're only returning the one that's larger, right? So the one that's smaller never gets returned up to the parent call in the recursive order. Right? Does that make sense to everyone? Like how we want to fix this? This is going to be important for the lab. Yes. Mm-hmm. Right. So 0 plus 1 would be 1. Does that make sense? So it doesn't really matter because we're both incrementing +1 here or +1 here, so it doesn't really matter if you do the +1 here or the +1 here, because you're depending on you're just comparing 3 and 4 or 4 or 5, same thing. Right? All right, and then E, where it's not we're 2 down, so we already know we can use this by elimination, but missing return after if then else is we don't really do it because we only return when we are doing when we hit the bottom, when we hit the leaf node and there's no more tree to traverse is when we start returning up and incrementing the edges and counts. Any questions so far? Any questions about implementation of the height function, why we use recursion, and how we do it correctly? All right, great. So let's move on. So when we're writing recursive functions, one thing that we want to make note of is that before we actually jump into the actual code, it's good practice to come up with pseudocode first, and then essentially use induction to convince yourself that it's correct. So in induction, you essentially have a base case, and then you have the inductive case. So recursion is essentially your recursive case is also your inductive case, where you're applying that same function, that same procedure onto a smaller part each time in the set. So that's essentially the way to go around recursion. And then if you actually do it in the base case and recursive case, and you think of it in terms of induction, it also makes it much easier to prove the correctness of it or validate your inductive hypothesis or recursive function. So check for base cases. Assume that it works for m, and then you have to show it works for n plus 1. That's essentially your concept, fundamental concept of induction, is that you assume that it works for n, and then you show that it also works for n plus 1. So in these cases, n0 is n1, and then n greater than 1. So this is essentially your base case. Back in the code. All right, so talking about recursion, we're given a problem that, given a binary tree that contains integers, you want to compute the sum of all the values in that tree. And the sum of an empty tree is 0. So first take a few moments and come up with the pseudocode for this. All right, so I'll give you, let's say, 4 minutes to discuss with your peers, think about it, and come up with some pseudocode that correctly implements the sum of all the keys in a binary tree of integers. All right, so let's come back and discuss what the pseudocode would be. Uh, so if the tree is empty, the sum is 0. So in this case, you've got the sum to be 0. Otherwise, you sum the root value uh, plus the sum of the left subtree and sum of the right subtree, right? So important thing to note is that there's no if-else conditional. There's no like in height, we were doing recursion for the height function, but we we had a condition where we either returned the height which was on the left-hand side or the right-hand side, depending on which one was greater. Right? So there was a conditional. So you can have conditionals in recursion, but in this case, we don't have any conditionals because we are concerned with the complete tree. We're concerned with it. We want to calculate, we want to sum up every single node. So in this case, when the root value is 22, what would be the sum? 22, and then the sum of left subtree and sum of right subtree would be 0 because there are no subtrees. So there would be a recursive call to this and a recursive call to this, but then those recursive call would return the base case, right? So think of each recursive call as a call on a smaller version of that tree. Is everyone clear on the pseudocode? All right, awesome. So let's quickly look at the actual implementation of it. So again, you've got the helper function that's underscore sum that where you're implementing the actual code. You've got an integer sum. You've got your base case, which is going to return 0 if this is 0. So this is going to return 0. This is your base case. Otherwise, it's going to return some current value, and in this case, it's going to be 22 because there are going to be calls to sum underscore sum for left and right, but what are left and right for 22? They're null. So the sum is going to be 0. So it's going to be 22 plus 0 plus 0, and it's going to return 22. But in this case, it's going to come out here. It's going to sum up 22. Then it's going to sum whatever's on the left-hand side plus, and once it's completed this, it's going to come back here and it's going to sum everything that's on the right-hand side. So how it would work would be 22 plus 11 plus 19 plus 0. And then it would start returning, and then it would come up here, and then it would plus whatever that sum was plus 49. All right. Great. Any questions? All right, awesome. So you should be working on attending your respective lab sections. Thank you.